Okay, so this one now, I'm going to continue about this general case. And I guess the bottom line of the equation is reaction to free energy is 0 at equilibrium, and because of the definition of delta G, we can do this. So this is a summarize what's going on thermodynamically, how the chemical equilibrium can be described. And is this concept about Q or K, I guess this is any composition or any extent of reaction, and whereas this one is at equilibrium, right? And we essentially want to say Q is now, instead of using the constant, we are using this notation. The products of activity with a constant mu J. So they just call it as activity of reaction. Activity products. And then I guess a K is nothing but, it's just you do the same operation, the ratio, the activities of reactants and the bottom, and this one goes to the top. A J mu J on the equilibrium conditions. So this is nothing but it is. So by using the notation where we have really the definition of thermodynamic equilibrium constant, something that is similar to concentration or the pressure. Okay, this is like for the gases, AJ is, you remember the PJ or pressure, and then multiply by it's not PJ actually. AJ is PJ for the gases, or sometimes people just want to use the molar concentration for the solutions, and they can use those terms, but conceptually it's always a ratio between the products divided by the reactant. So I actually have an example here to make you feel better. So this is actually a very famous reaction. So this is a gas phase reaction. Do you know what this reaction called? We exist because of this reaction. This is a nitrogen fixation. Right? So nitrogen with a hydrogen, you put it in a catalyst, you all of a sudden they make this ammonia. This is a Haber reaction and a Haber process, which is ammonia is an essential ingredient for making all these fertilizers. At the same time, the explosive too. Okay, so this process was developed during the World War I by this German scientist Haber. And okay, so once you guys know this, I think I want to know essentially I want to know my K, right? I want to predict the K. L and K is somehow related to this one, right? So my starting point is calculation of this, okay? So then I can easily calculate my equilibrium constant based on this. So this one is now looking at 2 times the free energy formation of this ammonia. Okay. So you're just looking at the information that you already can find out in the tables of thermodynamic properties. Hydrogen. So that's following the usual one. Product has a positive constant, and then this one is a negative constant. You calculate those from the heat of Gibbs free energy or the Gibbs free energy of formation. And do you remember this? Gibbs free energy of formation, heat of formation for pure substance, and the standard condition. This is 0. Okay? So it's actually, if you look at that, you will see the 0 numbers, and in the column that, I mean, this one is 0. Once again, just refresh your memories. This is 0 for those two. Only thing that is not 0 and we are not using the symbol is this one. This is not 0. Okay? But if people can tabulate those numbers when they measure the delta H and then they measure delta G using the actual K value, they can actually put these numbers back in. At any rate, what I can do is I look at the numbers, and this is a 2 times 16.35 negative kilojoule per mole. And so now minus 3.29 10 to the 4th joule per mole. And I want to actually make sure that this is not the same mole here. You see the mole here? The mole here? They are not the same mole. Okay? This mole is coming from these values, right? So this is a per mole of NH3. That makes sense, right? But what about this? This delta G is defined, I guess it's an energy, therefore I understand that, divided by mole. And this mole is this something called, we talked about psi, right? Psi, which is an extent of reaction that per mole basis. So because once you write this one, there's a, I guess it's same as a nitrogen, and this is there are 3 times more changes than the psi itself or the hydrogen itself. So we can, has a much more general. Okay, what, I guess the use of this is, okay, let me wait a minute. 0 is R plus RT ln K. I know that. So therefore, ln K is minus RT. You can do that. And then they're asking the temperature is 285. So you're putting all these numbers, so which is a minus before. This one is minus 3.29 4, which is joule per mole. The bottom is 8.314 298. It's negative, negative, it's positive, and you will get this number. Therefore, your K value here is exponential to 13.2. That is 5.4 10 to the 5. I mean, this, I guess for the PChem class, this one has not much of the meaning. But what I'm saying is, let me just keep, I only keep this one as only one value. So let's say this is about 500,000, right? That's about 500,000 at this temperature. You know what that means is this is a nice way for I can open up the question on the next chapters. When you mix the nitrogen and hydrogen at room temperature, the driving force tells me that they want to be ammonia. It favors, I mean, I kind of erase all the detail. Let maybe just say 500,000, it's like 1,000,000 times to the 1. Right? They really favor the production of ammonia. So, oh yeah, I learned from this. So you open up and then you open up the bottle, put the hydrogen, put the nitrogen, wait. Do you see the change? You don't. So that's really the fine print of the thermodynamics equilibrium. Equilibrium do not care about how long does it take for this to happen. It just say that what will be my final, I guess, the ratio between the products and the reactant. But they actually do not tell me that how long does it take it to get there. And this is why the kinetics. I want this one to be happening in an hour. That will be better than waiting for 200 million years, right? And so therefore they developed this. Thermodynamically, I know ammonia is going to produce. But how can I make this one faster? And that's why they developed this. Expedite the reaction. We call control the kinetics using the catalyst. And the catalyst is where all these big chemical companies make a living out of this. Okay? There is all kinds of different catalysts that are being developed.